Hi, my name is Justin Shrubbery, and today I'll be talking to you about the error performance analysis of adaptive orthogonal frequency division multiplexing, or OFDM systems. So we'll start with the overview of the system and the simulation. So the whole reason I got started in this is because when we discussed OFDM in the class, I was interested, and then I saw an avenue for the exploration of the adaptive modulation algorithm, and I'll go into more details about what that really means. But for this simulation, I chose to explore the additive white Gaussian noise channel and then a frequency select fading channel as well. And then this adaptive modulation algorithm strictly was focusing on the error performance and trying to optimize the OFDM receiver for the best error performance possible. So first, let's talk about some of the advantages OFDM systems have over other systems. The first and main advantage that OFDM system has is that they're spectrally efficient. They're a wideband multi-carrier system, and what that means is you're given a wide spectrum, and multi-carriers are located on different frequencies that can carry messages to and from to a transmitter and received by a receiver. And these subcarriers can all belong to one single user and be combined at the receiver to form a higher data rate data stream, which is actually what the OFDM system here does. Or these subcarriers could belong to multiple users, and each user is then given a slower data rate. But the OFDM system here, it actually allows some overlap between each subcarrier, so it's able to use half the spectrum as other frequency division multiplexing techniques. Because it's a such a wideband system, it performs well in fading channels, and with the subcarriers, you're able to slow each subcarrier down with the symbol rate, and that reduces the amount of inter-symbol interference, because you would then need a channel that has a longer coherence time in order to provide that same inter-symbol interference with a slower symbol rate. So the inter-symbol interference is typically negligible, and another advantage that OFDM systems has is it's an easy way to it's very efficient to be implemented, and so even if equalization needs to be done to remove any inter-symbol interference that is left, it's very easy to do that simply with coefficients that can be added to the implementation, which I can explain later. For this project, the PSK modulation technique was chosen. I could have used QAM or some other technique, but I was already fairly familiar with the PSK modulation, so it was easy to get started. But we'll just go through a brief overview here. This plot over here to the right is the theoretical PSK error performance for BPSK, QPSK, both of which have the same error performance, and then the 8, 16, and 32 PSK, all of which are in the AWGN channel. So on the left here, again, just a quick overview. The BPSK bit error probability. I like this plot. It's the top image here. It's easy to visualize what an error would be, assuming both symbols here are equally probable. You can give the Gaussian distribution to each symbol, and the detection line is just to the left of 0 to the right of 0, and your error is the error under the curve for the under the wrong distribution. So that's where you come up with the theoretical bit error performance for BPSK and QPSK, both of which have the same error performance if QPSK is given twice the energy. BPSK is a one-dimensional signal space, but then QPSK and above all have the two-dimensional signal space. The 8, 16, and 32 all refer to are referred to as the modulation order, and all that means is more bits are encoded into the symbols. There's for QPSK there'll be 4 symbols in the signal space. 8 has 8, 16, and so on and so on. And then you encode the bits into those symbols. The problem with the higher modulation orders in PSK is there's no real easy closed form way to express the error probability, so you actually have to look at the symbol error probability, and then depending on how you encode the bits onto those symbols, that will affect your error probability as well. So now let's talk about the adaptive modulation algorithm. This is really the key to this project and distinguishing it from just a OFDM analysis. But what the adaptive modulation algorithm tries to do is reduce the effects of a frequency selective fading channel. So over here in this plot you can see the profile, it's the magnitude plot of the frequency selective fading channel. So you can see some, all down here. If your subcarriers would be located at these frequencies here, you would actually, it would be detrimental to the system. The system would be dominated by the poor error performance of those subcarriers, because the chances of receiving the right symbol on those subcarriers would be poor. Whereas if you could transmit more up on these subcarriers that have constructive noise there, that would be optimal for your system. So what the adaptive modulation algorithm does is basically take a look at it looks at the profile here, and then comes up with the modulation key and limits the amount of energy and time spent in the spectral nulls, and tries to increase the amount of information sent in all these in the higher magnitudes of the channel here. So all you have to do to really figure this out is take the magnitude of your channel and multiply by the SNR, and you will be able to figure that out. So and then down here, this is the table we used or I used for the simulation. Once you get your threshold metric for the channel, you can simply look it up into this table, index into it, and see where you fall. And if you and then you're able to come up with your modulation order for the system. So the hard part would be in actually implementing a system like this is, how do you get the channel profile like that? But for the simulation, we just wanted to look at the gains and determine what the gain was from, if you had this information available, what kind of gains could you achieve? And then this table here is basically taken from the AWGN results that you saw previously. You can look at certain points, and you can choose the point that you want to optimize for, and you basically choose those values based off those theoretical plots. And then other research was noted, and those are similar numbers used in other research as well. So here's the system diagram for an OFDM system, and as you can see, it's a simulation. Starts off with the configuration for what we're going to run, and then we generate that's the data generation here. And as you can see, there's a preamble and random data, converts it from serial to parallel, and this is the key for an OFDM system. This is this block here in the transmitter, and then the same reverse block in the receiver is really what makes the OFDM system. So it takes a serial data stream, converts it into an N parallel stream, is a size N, which is basically the size of your FFT that you'll use, or inverse FFT that you'll use as well. And so this can vary. If for our case, if we're using this adaptive modulation algorithm, each one of these M-ary PSK modulations will vary. The order will vary based on the adaptive modulation key that is created from looking at the channel profile that we discussed earlier. So you have all these individual modulators essentially for each N subcarrier, and then you run those N subcarriers through your inverse FFT function, and you can mix it up to your carrier frequency, and that's the simple, efficient implementation of the OFDM system. And so then for this simulation, we would run it through the AWGN channel or the frequency select fading channel based on whatever configuration we were set for in the beginning. And then we would run it, once it's done with that, it would go through the equalizer, and this is all in the receiver now. It goes through, we would assume ideal equalization, just run it through the same size FFT in the receiver to undo the inverse FFT function, and then you're left with N subcarriers again in the frequency domain. So you have to use the same adaptive modulation key, is what I refer to it as, that is used to tell the receiver and transmitter which modulation order is used to demodulate or modulate those individual subcarriers. And then you make the decision here in this subcarrier. For each individual subcarrier, you'll make the decision, decode them into the bits, and then recombine from the parallel subcarriers into one data stream. And so one of the things that was noted throughout the simulation that did give most trouble, you'll see this preamble and data synchronization, and we'll come back to that later and discuss why those are needed, but those were added in this simulation, and we'll talk about that later. But as you can see, the key here is this sharing of the information for, it's the sharing information of this adaptive modulation algorithm. That is really what makes this simulation different from just a regular OFDM system. That is the adaptive modulation portion.